Welcome back everyone to a lecture about applied bioimage analysis. This week will be about machine learning and especially about machine learning in the context of pixel and object classification for microscopic images. So just as an overview, I will give a very broad introduction to machine learning in general. We will have a close look at how random forest classifiers work. And we will also have a close look at how to evaluate how good an algorithm is, because that's actually part of the story, an important part of that story. We will have a short look into deep learning. And then I will introduce you to some tools which you can use for machine learning, some plugins in Fiji, and an independent software called Elastic, which is, I would actually say, more powerful than all the plugins we have in Fiji together. So just as a recap, so what we did so far, we took an individual independent image, we processed it in whatever way, and then we came to a binary image. And it already, while doing so, it turned out for us that going from an original image to a binary image and going from a processed image to a binary image results kind of in different binary images. And which of the binary images is the best one is the thing we are doing. We are trying to find out while setting up the corresponding workflow. So there's different inputs leading to different outputs, and some outputs are better than others. So obviously it's like us making a decision here on how to come to the best possible segmentation result. It's us who subjectively make a choice for a workflow which leads from an original image to a binary to a segmented image. And the next step actually would be, and we already did it last week, at least I showed you how it works in general, and we combine several images and bring them together in one image and then derive a solution from this one. So for example, difference of Gaussian, we blur the image with two different sigmas and then we subtract the one from the other. And we get an image out which might be better to segment or easier to segment, and derive a binary image from that. So we have many different Gaussian blur images we can put in such an algorithm, and we can subtract them from each other. We can combine them in a linear way to get an even better segmentation result out. And it's still us making this decision on which of these images to take in order to get a good segmentation out. So that brings up the question, might there be a black box where we can just throw any kinds of images in which come to our mind, so the original image, the blurred image, then the one blurred image subtracted from the other blurred image, and I mean really many of them. And can this black box maybe tell us how to combine these images in an optimal way to come to a binary image which is really a good segmentation? So can we please get rid of this task of modulating the workflow by hand? Can we please have a software which helps us with that? And the answer to this is machine learning. And before we dig very deeply into machine learning and how a particular algorithm in this field works, let me make a point here. So machine learning is still an active research field in computer science. It's a subfield of artificial intelligence. And there is, of course, many applications upcoming. Also in Fiji, you find more and more plugins, like for example, the trainable vector segmentation in Fiji, LabKit, or independent tools like Elastic. That's the tools we will have a look at today. But always keep in mind, this is still, at least to some degree, research. So if you see a nice video on the internet where some researchers show amazing things you can do with machine learning, it might be true that you can do these amazing things with machine learning, but it does not mean that everything is applicable to any kind of data. So unfortunately, from my perspective, machine learning has a lot to do with expectation management. There's a difference between what researchers in computer science do and what people like me, image analysts or biologists in biology can use. So there's a there's a difference between these two opportunities. Furthermore, a subfield of machine learning is then deep learning, and that's even more researchy. So also here there is some plugins coming up for the applied scientists who just want to use it. So for example, here you see a Fiji plugin which is actually pretty new, and it does denoising, so like a median filter like we did earlier, but much more sophisticated. And when you look here at the original image and when you look at the denoised image, you may agree that this looks like a super fantastic denoising result. So we can replace the median filter by noise to void. And unfortunately, it's a lot more complex and a lot more complicated than a median filter. So not for every application, for any kind of image, coming from any kind of microscope, noise to void might be the right way. So that's why I'm again saying, so this is still part of active research, and which deep learning based algorithm can be applied to which image to get what out is still part of research. Then you have more sophisticated plugins, for example, for segmentation, like Stardust. Also, this comes as an ImageJ plugin, and there is a platform called Deep ImageJ, which actually aims to deliver various kinds of deep learning models to ImageJ to Fiji users. So maybe also check this one out. I'm just mentioning here a handful, and I think the number of algorithms is exploding these days. So if you watch my video here in half a year, you may say, oh, okay, these 3 things are super outdated because there is no new stuff. There's a huge momentum in this, on the research side, but also on the applied science side. Your new plugins for stuff like that are popping up every year these days. Okay, but maybe one step back. So we will not look very deeply in deep learning today. We will mostly concentrate on the more general part, machine learning. So let's step one step back. What is machine learning technically doing for us? So assume we have some kind of raw data, and we now want to come, for example, to a classification of this raw data. Therefore, we need a model. The model is kind of an abstract representation of what is there in our raw data, and it allows us to do a prediction from the raw data to, for example, a classification. And just to give you some examples of what that might mean, we can start as raw data. Yeah? So we can start from pixels, from individual pixels or from group of pixels combined in images. We can also start from segmented objects in images. That's actually quite practical. But we can also take a whole image and throw it as raw data into a machine learning system. But furthermore, also audio, text, any kind of measurements, whatever. Yeah, so data in very general can be put into a machine learning algorithm, and then the algorithm predicts from that kind of data. So, for example, if we start from a handful of pixels, it can generate for us binarization. So that's the term you know already. Binarization is making a binary image out of a gray value image. And machine learning researchers also sometimes talk about so-called dense segmentation. So you segment the object, the thing in an image. And if you talk about differentiating different objects in one image, so that's what we call as connected components analysis or labeling. The machine learning researchers talk about an instance segmentation. So we are segmenting different instances of the same thing. So assume in our original image, we are looking at a super bad resolution at 2 nuclei. Yeah? So this is 2 nuclei. And the algorithm, the machine learning algorithm, can differentiate both instances of nuclei. And that's why it can mark, for example, both in different colors. So that would be an instance segmentation. What we can also do, we can, starting from the objects, we can make an object classification and, for example, say, okay, we now differentiate the objects which have a certain size and objects which are too big or bigger or have a different shape, right? So we differentiate for object properties of segmented objects in an original image. And maybe the most classical thing which comes to your mind when you send an image like that into a machine learning algorithm, and the algorithm can tell you that it's a cat in this image. So this is kind of the classification of the whole image. The algorithm tells you what is in this image. So this can be a kind of a class. That's where the term classification comes from. Yeah? So it's a class of thing. It's classified. It's something in a certain category. But it can also be a continuous quantity, for example, a probability. The probability of a cat being in this image, so the probability of there is a cat in the image, is 0.5. But when you look at this image, there's also the probability of a microscope being in that image of 0.4. So you can actually get continuous variables out of a machine learning algorithm, which tells you the probability of something being in there. It's true for pixels, that's true for images, that's true for any kind of classification you can do. And last but not least, the big art, what computer scientists try to achieve these days, the big art of machine learning is getting a complex measurement out of an image. So for example, this cat has a height of approximately 80 centimeters. So, and if a machine learning algorithm can derive that from an image, that's like, yeah, So we could replace the whole image processing workflow, the whole pipeline from pre-processing, segmentation, post-processing, measurements, and so on. We could replace all that by a machine learning algorithm. So I'm pretty confident that this will happen, but I'm not sure if it will be in this decade. So there's a lot of work to do in order to get algorithms to that point. But many people aim at that, and that's why I'm mentioning it here. Getting a physical property, a measurement of something from the real world out of an image, which just shows a perspective, a certain part of the real world, that's the big challenge in machine learning, or at least in bioimage analysis related machine learning where the people are working on. So the question is now, how do we get this model? If we have it, if we can do this prediction, awesome. But how do we get it? And therefore, we need annotated data. So annotated raw data, usually annotated by humans. So in order to know that in this image is a cat, we have to provide to the algorithm which does this model generation. We have to provide to the algorithm hundreds of images showing cats and thousands of images showing no cats in order to train this algorithm to be able to differentiate between cats and no cats. So what's also important, it's actually part of the training, but it should also be part of any workflow afterwards of anything happening after you used machine learning for analyzing your data. You should always try to find a way how to measure the quality of what just happened. And there are terms like precision and recall. We will later look deeper into what they mean, what these measurements of quality mean, and how you can derive them from your data. They are important in order to know that my algorithm is really doing what I expect the algorithm is doing for me. Because it's not that I specifically write down an algorithm to come from this to that. It's more like, computer, please find a way for going from this to that. And then afterwards, we have to check carefully if it's really doing the right thing or if maybe there's a misunderstanding between the computer and me. So the goal in principle for, let's talk about classification a bit more in detail. The goal for classification based on machine learning is we want to classify, we want to split our data points, which we get from any kinds of measurements, and we want to split them in different groups. We want to say, okay, this data point is rather from that category. It's an image showing a cat. And this is a data point which rather comes from a different category. It's an image showing a microscope. And therefore, we have to have certain kind of input parameters. So, for example, this is a two-dimensional parameter space, and we have an x-axis and a y-axis, and we have data points in our diagram. And now we have also ground truth. So the ground truth tells us that the data points more in the upper left region were usually red, so that's images showing cats. And the lower right corner, that's where rather images showing no cats, and that's why they are marked as blue here in this area. And what's on the x-axis and what's on the y-axis doesn't matter for the moment, yeah. So it's just like we have different measurements spanning our parameter space, and here in this case, it's a two-dimensional parameter space. And we can now take different algorithms, for example, so-called linear support vector machines. I will not dig deeper into this, but that's a very simple, a rather simple algorithm which takes the data points and derives a vector. So a vector is like an arrow pointing in a direction telling us, yeah, in the upper right corner, it's more likely to be an image showing a cat. And when you invert the vector, so the vector shows in a different direction, so then it's rather images showing no cats. So this is what the color here tells us. So the upper left, there's something, and the lower right, there's something else. So two different classes. So this is how you differentiate two different classes with a support vector machine. And again, we will not dig deeper into this algorithm. Then you can make a so-called decision tree. Decision tree divides the whole parameter space basically in rectangles and tells you, oh, in this rectangle, it's likely a cat. And in this rectangle, it's likely no cat in the image. I will show you in more detail how this one works. And when you take several decision trees and put them together in a bigger system, you get a so-called random forest. And a random forest is kind of a combination of many decision trees making a kind of sophisticated decision, which is not so fixed, which is a bit more flexible. The whole thing is a bit more robust against variations in your data points. So, and that's the tool we will have a close look today. And furthermore, so this is by the way from the scikit-learn website. So that's kind of a library of machine learning algorithms. dependent on what you want to achieve and dependent on computational resources, you can take any kind of algorithm. I mean, look at all of these. They all have different properties. They are differently fast, they are differently precise, and depending on what you want to achieve, you should pick one particular algorithm. I will show you today just the random forest because they are very popular in image processing, and I think for a reason. But you should at least be aware that there are many, many alternatives to this kind of algorithm, which serve the same purpose, but for different domains. So that's just letting you know that there are potential alternatives to this one. If we talk about machine learning in the context of image segmentation, we usually have a ground truth, or we can make a ground truth. So somebody can sit in front of the computer and outline some regions or generate a binary image in whatever way. And we can take this binary image as ground truth for training an algorithm. So, and that's what machine learning says. And when we give to the algorithm some kind of ground truth, a binary image as a starting point, so this is what I perceive as right. So now please find a configuration of your algorithm, find an algorithm which solves this segmentation problem in a similar way as I did. That's learning, and it's obviously supervised machine learning because we gave something, a ground truth, to the algorithm, and that's why the algorithm can come up with a potential solution. So that's the term training. So we give to a black box, we give a binary image, we give some raw data, and then the black box comes up with a potential prediction algorithm, which can make this decision for us. If a pixel, for example, a pixel should be rather white or rather black. So I take, for example, this particular pixel from here, I put it into my black box, and the algorithm inside there can make a decision if it should be white or black. And then we put this white or black pixel in our resulting binary image. If we go the other way around, if we go from the binary image in this direction, then the terminology says that this is the training step. So usually we do training first and then prediction afterwards. And ideally we do prediction on many images and training on not so many images, because otherwise it does not make so much sense, right? And again, we will today use in very detailed decision trees and random forests. So what is a decision tree? A decision tree is a classifier, so it's an algorithm which can make a decision if, in order to put something, a measurement, a sample, into different classes, into different categories. For example, it can decide if a pixel should be white or black. So that would be a binary classifier. Random decision trees are randomly initialized and afterwards evaluated and selected. So this is a decision tree. A very small one, actually. So we start from the bottom and we come to a point where we inspect. So here in this case, we inspect a green value. Yeah? So a green feature, actually. And depending on if this feature is large or small, we can say, okay, the pixel should be rather white or rather black. So this is a kind of a binary classifier for a pixel. And there can be many decision trees put together, and they can also all look different. So they also can have different depths, for example. So depth in this case, the number of decisions which have to be made. So here this one takes a pink measurement into account and the blue measurement into account, and it can then decide if the pixel should be white or black, right? And if you put many of them together, we have a random forest. And let's look into this a little bit more in detail. So we have our original image. It has two channels. It's a green channel and it's a magenta channel. And we have a binary image, our ground truth. And I will now put individual data points into this plot, which represents the intensity in the pink channel and the intensity in the green channel of this particular image. So let's start. I took this one data point from here. It's obviously pink and not so green. That's why in our diagram, where we see our intensities in the two channels, we see this dot over here. Then I take another point which is rather green and not pink, and we put this data point here. And you see when I now move from the data point where I took it from, so it's somewhere here, or when I look at this data point, which is obviously in the center of the white object, we can color these data points in white or in black. Yeah, so I take just the third one from the white area. This is like it's pink and green kind of, and that's why we have to put it here in our diagram. Now we start with some black data points. So obviously this is a region which is outside of the white objects. Yeah, so there's also neither pink nor green, so that's why we put it in the bottom left corner of our diagram. and we annotate it, so that's kind of the binary annotation, so it's black. Yeah. And let's go ahead. There's also a data point here, which is like a bit green and a bit pink, but still black, so that might be somewhere over here. And there is another point, which is rather green and not so pink, but still black. So this is how we get this initialization of our samples, of our randomly sampled data points from the original image and a corresponding ground truth image. So and again, this selection of data points, which we take into account for building our random decision tree, is random. So we pick kind of a handful of pixels from our original image and from the ground truth, and we sample data points like that. If we now would put an individual threshold, for example, on the magenta channel, we could not differentiate the black and the white data points correctly, not all of them, right? So the likelihood that all white points are on the right side and all black points are on the left side is limited here in this particular example. And that's actually true for both channels. So again, in this particular example, right? So it is not possible to draw an individual line, even if the line looks like that. It's not possible to draw an individual straight line into our parameter space to differentiate the white and the black spots from each other. So in this situation where you cannot put an individual threshold, then you may want to go for a random forest. And it works like that. So I start building up my decision tree. So my tree will now grow from here. The root is already there, and I will put an individual decision there, which is a threshold, right? Saying, okay, if the intensity of my data point is larger than 0.6, then they are all white, right? And I can write that down in my decision tree. If I now want to describe the data points on the left side, I have to make another decision. So it's not like they are not all black. There are black ones and there are white ones, and that's why I have to make another decision. So for example, if I say, if the intensity in the green channel is lower than 0.8, then they are black, and if not, the remaining ones are white. So this is how a decision tree with random samples out of my original image with ground truth is made. And now I take a new sampling, so I sample other data points from my original data set, and I build up a new decision tree for this particular sampling. So now again, we start at some point, for example, this time, we start with the green channel first, and we check if it's smaller than 0.3, so that's all data points below this green line. It's obviously the data points are all white. If it's not smaller than 0.7, so that's a bit like if it's larger than 0.7, so if it would be a yes here, so then they are all white. So that's these guys over here. And for the remaining ones in the area in between, we still have to make a third decision, which is kind of if my magenta channel is larger than 0.4, it's white, and smaller than 0.4, it's black. So this is how decision trees are built up from a random sampling, right? And we do this hundreds of times and make a lot of trees for building up a forest. And then we have our forest. So I have here my decision trees. And as features for this decision tree, we take differently filtered input images. So you see here, for example, this might be my original image blurred with a small sigma. This is an image, the same image actually blurred with a larger sigma, a Gaussian blur, and this is the one image subtracted by the other one. So this is the difference of Gaussian, for example. So we put different images which were pre-processed in a different way. We put them as input for the random forest, and then we take individual pixels, but at the same position, right? In these three images, we take 3 pixels out of that and do this a couple of times. So we do that for different pixels, and together with a ground truth, we make a selection. So some of the trees may, so we have randomly built up trees, and we are now again randomly sampling from the original image, and we are comparing how good these trees are in making this particular decision correctly according to the ground truth. So we can now differentiate the good trees from the bad trees and make a selection. So we kind of kick out of our forest, we kick out all the trees which are not good for making this particular decision. And this selection process actually means that we have to find a way for differentiating the good decision makers from the bad decision makers. So we have to evaluate how the decisions they make overlap with the ground truth. And therefore, we have to do some sophisticated algorithm evaluation. And we dig a little bit deeper into this now. So far, we were talking about binary images, which have two conditions, positive and negative. So positive usually is white, negative usually is black, at least whenever I talk in my slides about it. And we changed it now a little bit in order to have more categories possible. So positive, green, no, still something we can have in mind. Negative, white. So this is the ground truth. This is what some human annotated, where he is sure about that this region over here is positive and all the other pixels in our image are negative. Yeah, so this is kind of ground truth. And we now apply an algorithm to this, and the algorithm comes up with a different solution. So the algorithm thinks that this is positive and this is negative. So it's obviously not the same. So we now want to evaluate to what degree the algorithm and the ground truth actually set the same. So this is what we now do under the headline algorithm evaluation. And therefore we draw a bit more complicated diagram showing the overlap between these two regions. And now we have to differentiate. We don't have just positive and negative anymore. We have to differentiate now in true positive, true negative, false positive, and false negative. To start at a simple point, we start at the center. Here in this particular region in the center, the algorithm was convinced that this is part of the positive region, and the human who generated the ground truth also said that this is part of the positive region. So that's why this is true positive. So the algorithm and the ground truth overlap here. So that's why this is true positive. Outside of that region, so this was actually positive in the ground truth, but the algorithm didn't see it as ground truth. So the algorithm has here false negative findings. So the algorithm thinks it's negative, but it's not true. So it's false negative. That's where this term comes from. On the other side, the algorithm thought that this is positive, but it's not. So it's false positive. And this is how we write down this this kind of terminology in parameter space. Again, this is two-dimensional parameter space, but it can be anything. Furthermore, what's in the very most evaluation techniques not so much taken into account, but you should at least know that it exists, is the number of true negatives, which is kind of the region which is neither here nor there nor there. So that's all remaining pixels where algorithm and ground truth both said, okay, this is negative, true negative, right? By the way, welcome to the theory of sets. This should be something most of you should have heard in school earlier. It's just a refreshment here and kind of bringing particular terms for machine learning algorithms into your head. But it's something you can actually read up in math school books. So if we now want to know which fraction of points were predicted as positive, which were really positive, we call it, this measurement is called the so-called precision. And we divide the number of true positives by the number of true positives and false positives together. So this is kind of the math behind precision. And there's another term, it's called recall. I also know it as sensitivity. So what fraction of positive points or positive samples were also predicted as positive? So that's a bit different. It's the number of true positives divided by the number of positives in the ground truth. So that's true positive plus false negative. So we basically divide the true positives by the whole green region to get sensitivity or recall, and we divide the number of positives by the whole pink region to get precision. So this is the two measurements which tell us something about the quality of the algorithm. And what's kind of important here, when you play a bit with these measurements, you will realize that later on, that neither the one nor the other tell you everything about that algorithm. You have to take these numbers, both of them, into account in order to differentiate good algorithms from bad algorithms. So there is algorithms which are super good in precision and super bad in recall. So as simple as that, right? And you want to have an algorithm, you want to have a classifier, a decision maker, which is kind of good in both of them. Otherwise, they are worthless, let's say. Let's have a look at some practical examples and let's see how one can actually measure that. Let's assume we are talking about pixel classification. So that's why we are talking about the pixel-wise segmentation quality. And we have now here So the ground truth was actually the green area over here. Yeah, so it's nine pixels were ground truth, and we have a segmentation result which outlined these 6 pixels. So our segmentation algorithm said that the object sits here, and according to the ground truth, it's a bit bigger and it's sitting in a little bit different position. So that means that these are false negatives, these are false positives, and there where the algorithm and the ground truth both agreed that there is the object, that's the so-called true positives. So let's now count them. So the number of true positives is obviously 4. The number of false negatives is 5. The number of false positives is 2. And from that we can calculate precision. So precision is the number of true positives plus the number of true positives divided by true positives plus false positives. So that's in this particular case 66%, and the recall is 44%. If we talk about not about pixels, but if we talk about objects, we have to think about some kind of it's not segmentation, it's actually detection. It's like finding these objects and classifying them correctly. That's why I call it here detection quality. So we have so obviously the ground truth was a definition of these 4 objects, because the white ones are magenta and green, right? So this is kind of these 4 objects were ground truth, and our algorithm found these 5 objects. And so there's three true positives where ground truth and segmentation result overlap. And there's 1 false negative over here and 2 false positives on the other side. And we can count it again. So we have 3 positives, we have 1 false negative, we have 2 false positives, and that results in 75% precision and 44% recall. So this is kind of, you should not have these formulas in mind all day. People Google that if they need that, but you should know how to take such a formula and such an image and to come up with a proper calculation of false positives, false negatives, precision, recall, right? So this is something one should know. Furthermore, in practice, it's a bit more complicated. Let's assume we have a segmentation algorithm, which is also which is kind of finding objects and not just classifying pixels. So in practice, in order to determine the quality of such an algorithm, we have to think a bit more complicated. So let's assume, again, ground truth, green, and what the segmentation algorithm did, the prediction in magenta. And now there's overlap. So for example, if you see here, this particular object obviously 100% overlaps. That's why it's white. Also here, between what the algorithm did in magenta and the ground truth in green, the overlap is pretty large. So that's why this huge white area is there, and we could actually count this object as, yeah, okay, the algorithm found it. It's not perfectly outlined, so the outline is not precise, but the detection is good, so it classified this object correctly. And here in this region, the overlap is not so big. And that's why we should rather call this as a case where the segmentation did not work properly. And now, how do you do this from a mathematical point of view? We introduce another measure. It's a measure of overlap between 2 objects. It's the so-called Jacquard index. And the Jacquard index is kind of a mixture between of precision and recall. And also the Jacquard index is not perfect, right? So we divide the number of true positives by the whole area, which is spanned by true positives, false positives, and false negatives. So this is what the Jacquard index says. And then the terminology for measuring the quality of an algorithm would approximately look like that. We count the number of objects which at least overlap, according to the Jacquard index, by 50%, and then we count them as true positives. And if this is not the case, we count them as false positives and false negatives. And then we end up with a precision of 40% and a recall of 50%. Yeah, so this is just to show you how in practice then this is applied to segmentation algorithms. And there are more metrics. And depending on what you're doing, the one metric might be more interesting than the other one. So for example, when you talk about, so far we were classifying pixels, and we said this pixel is part of something and the other pixel is not. And we are talking about the outlines around the objects. and we want to compare the outlines, then maybe the contour distance may play a bigger role. So for example, in radiotherapy, where the outline around the contour is really decisive when it comes to do we hit the tumor when we irradiate it or don't we? Are there some cells outside of the irradiated region? Then the contour distance plays a much bigger role than the degree of overlap. Yeah. So just saying there's more metrics like that. I will not dig into deeper here. If you look for some alternatives, we can come back to this slide here. Or yeah, I mean, again, there's many ways of doing this. One important thing, so far what we did, we had one image and we had the ground truth corresponding to this image. And we were always measuring kind of between these two images. What is actually important to have in mind is when we train an image, when we train an algorithm, model on one image, we later want to see if it's also able to process different images. So for example, and that's important because if it's not the case, if my algorithm can only process the individual image it was trained on, then it's kind of not really like worth using because then I can outline my image manually anyway. I have to do it anyway for the training. So if an algorithm is able to make an abstract decision, to abstract a decision on a different data set, that's an important measurement. And therefore, we do the following. We start from the ground truth, from our training set, and we make a prediction. And then we train a model for making a prediction. And then we take this model and apply it to a different data set. So we take this classifier and apply it to a different data set. And then, according to the ground truth in this different data set, we measure how good it was on processing this different data set. And the machine learning experts talk about dividing the set of images into two sets, the so-called training set and the so-called test set. It's hard to generalize, but usually the training set is larger than the test set. Sometimes the people also divide into three sets and then balance between them. So there's again different ways of doing that, but I'm just mentioning here in order to find out how good an algorithm is making decisions on images it has not seen before. That's decisive. That's something we want to achieve. We want to have a classifier which can process many images and not just the one it was trained on. And this is how you can actually evaluate it. And when you think about how the math behind is done between comparing some ground truth with a prediction, that's exactly the same stuff as I just showed you on the slide before. Yeah, and typically this is done on thousands of images and not just on one image, the training, and on one image, the measurement of the quality. So I mean, machine learning makes sense with a lot of data, with a lot of images in order to find proper information about how good these things are. So that's the slide I showed you earlier. We have now learned how to separate the good trees from the bad trees. So we cut the bad trees and we keep the good trees in our random forest. And then we can take this random forest for making actually a decision on the pixel. And the question is now, how can we combine different decisions made by different trees in making one decision? Yeah. So I have now, for example, this one pixel having three different intensities in these three different images. So differently blurred images, for example, and we put it into our random forest. And our random forest, for example, comes to the conclusion, so two of these three trees come to the conclusion that this pixel should be in the binary image rather black, and one tree says that this particular pixel should rather be white, and the majority, for example, be. So this is kind of one way of how one can do this, and I would actually say that's the most applied technique for kind of in a democratic way asking these trees on making a decision for this particular case. Yeah, furthermore, the whole step of I take an individual pixel from an image it was trained on or not, and I give it to the random tree and the random forest, and the random forest makes a decision on it. This is the step is called prediction. To give you some numbers a bit behind, so when I learned this, I was a bit wondering about, okay, how are the quantities behind it? Does a random forest consist of 2 trees or 3 billion? So I wasn't aware. So then you can check a bit the literature and talk to experts, and then you will roughly find out things like that. So when we talk about features the trees can be generated from it's typically a rather large number. So it's something like 20 or 100. So it's like we don't produce one image. We don't take the original image and a Gaussian blurred version and a difference of Gaussian and have three images. Usually we take 20, 50, 100. So this is kind of the order of magnitude here. That's the features which are available for generating these trees, these decision trees. And how deep such a forest should be is usually less than that. So building a tree which takes 20 features into account may not make so much sense because we have many trees and these many trees all take different feature sets into account. So usually the depth of such a tree is smaller than the number of available features, and that's why also the number of selected features is smaller than the depth. What's also possible in these forests is that you take the same feature twice into account. So that's technically possible, and it absolutely makes sense. So, I mean, the algorithm just does it, and you don't look at this anymore afterwards. I'm just saying here that the number of selected features in one tree can be smaller than the depth of the tree, so the depth of the decision, kind of. And furthermore, the number of trees is usually something like 100, 200, 500. So the point behind is if there is one tree making a wrong decision, or if there are 30 trees making a wrong decision, that's not a big deal. It's not a problem if there are 70 other trees making the right decision. So that's the cool thing about random forests. That's why they are so powerful. And that's why they are so robust against different kind of input data. We have many decision makers coming to a democratic conclusion, kind of, and some of them can be wrong, and it's absolutely okay for the general result of the thing. So this is the power of random forests, actually. And that brings us actually to the point where we ask, okay, what else can we do with these kind of random forests? So what I showed you earlier, so this was my input image earlier, and we spanned this sample space in 2 dimensions. So I called the axis x1 and x2. But in fact, what you were looking at, we had on the x-axis the intensity in the original image. That's blobs.gif. You have seen it 100 times because I'm showing you the same image all the time. I was making a Sobel image, so that's an edge detection filter out of it. So this was the second channel, the green channel. It's basically the edges in the blobs.gif. So these were the two channels we put in there, and we did some pixel classification, some segmentation of this particular original image by taking two different measurements into account and by training a random forest, for example, for segmenting that. If we now replace the axis by something completely different, like not pixel related anymore, not pixel intensities, but for example, the aspect ratio and the circularity of our objects in this image or in any other image, right? We don't have pixel intensities here anymore or from kind of blurred images. We have now physical properties of a measurement of objects. So that's why we don't do pixel classification anymore. We do now object classification. But key point is the algorithms behind are exactly the same. We're just changing the input and of course the ground truth. But what happens in behind, how can the algorithm now differentiate different objects is the same. It just takes aspect ratio, circularity, area, position, right? Anything into account which is a measurement from an object. And when you do object classification, so typical applications is something like shape differentiation. So if you, for example, we have here on the left side, we see outlined objects. And we have some ground truth annotation. So I tried to differentiate the objects which are roundish from the objects which are not exactly round and maybe even several objects glued to each other. So I want to have a good measurement for cell nucleus size, for example, and therefore I have to differentiate clumps of cells from cells so that I can only measure the size of cells. So that's kind of the goal I want to do here. So if I want to make a proper prediction out of such a data set, I have to select the right features. What I'm saying here is that feature selection is key in machine learning, and you as a human are doing this, right? So, and if you want to differentiate for shape, it's kind of obvious. that you select the shape descriptors in this dialog. So later we will do this in Fiji, and so I will show you how this works in more detail. But here I'm just saying, if you want to differentiate objects by shape, you should say all shape-related features should be taken into account. And then it can make a nice prediction. What is a bit dangerous here is you should not measure in a quantitative way afterwards the shape of these objects, because you were excluding objects according to their shape. So if you afterwards measure their shape and say, they were all round, it's like, yeah, it's not exactly true, because you were excluding some which were not round. So that's kind of, if you want to measure shape, you cannot use shape as criterion for differentiating the cells you measure and those you don't. So that's a bit the danger here and behind it. It's like there is some machine learning tools out there which do the feature selection for you, or where there is an automated default feature selection. And if you don't read this and then you do measurements afterwards, you may hit a wall here which you don't see. So be a bit careful about feature selection. So it's like there's a different way for doing the same thing on the same data. I would like to exclude all the cells which are too large. So for example, I could now select the area as a criterion for differentiating cells. And it's like super nice to differentiate correctly now all the individual cells from the cells which are kind of actually clumps of cells. But it's scientifically not nice afterwards to measure the area of them, because we had the area as criterion for excluding some of them and keeping others. So that's what I'm saying here. The brute force method may also work. So you just select all features, and then it can make a nice differentiation between the individual cells and the clumps of cells. But be very careful about that. You do not, so in this particular one, when you sit in front of the screen and you look at this result, you do not know what the algorithm was actually taking into account. You would have to inspect the model now in very detail to find out what it was relying on. So, for example, what would be possible is that the algorithm did the following. It looked for the X and the Y position of the objects and realized that in the top left corner they should be all pink, and all the other objects in the other space they should be green. And that would mean that it did neither take shape nor area into account. It just took the position of these objects into account. And that would also mean if you apply it to the different image, and the clumps of cells are in a different area, it would not work. So the brute force method of just applying the random forest to all parameters you can get is possible and also makes sense in some scientific fields to figure out specific properties. But be careful about that, especially for making decisions on objects to take and objects not to take. We don't want to use the brute force method. And that actually brings us to the so-called unsupervised machine learning. So what if we have no ground truth? What if we don't know how to differentiate objects of different kinds? So maybe we have a rough estimation. We roughly know how roundish and not roundish objects are differentiated, but we don't know which particular feature is good for that. We want to find, so we would like to ask the software now, dear software, please tell us which parameter is good for making a certain decision, and we are not even sure about which cells are roundish and which cells are not roundish. Please tell us what you think. That's unsupervised learning. So we don't hand over a ground truth, we just look at measurements, and we use actually statistical methods for evaluating the measurements. So this is now our parameter space. It's aspect ratio and circularity. And we now measure from the objects we had in the image before, for example, we now measure aspect ratio and circularity of these objects, and we put it in our parameter space in this plot here. So from the first and from the second data point, you can say, so likely if the aspect ratio is higher, then also the circularity is higher. But concluding from two data points is like really not a scientific method. We don't have enough data yet, so let's get more data. This still holds true until some point where it's no longer true, and we get more and more data points, and it becomes more and more unclear, kind of. What is actually the relationship between aspect ratio and circularity? Is there actually a linear relationship, as we just thought a minute ago? Maybe there is not. So what can we get from this kind of data? And there is always a point where you say, okay, I still cannot conclude something from here. I need more data. So let's get more data. And there's also methods for finding out how much data you actually need. But for now, we will keep it like that. And at some point, so you can do this all the time. You can all the time ask the algorithm of what it thinks about this data. But what it does in the background, it measures the likelihood, or it measures the frequency of objects having a certain circularity. How is this diagram called? Just think about it. It's a histogram. Yeah? So the likelihood or the frequency of objects having a certain circularity is drawn here in this bar graph. So there's not so many objects with a high circularity, and there's not so many objects with a low circularity, but there are many objects which have this intermediate circularity. Like here in the middle in this graph, there's a lot of data points. And now we do the same thing on the x-axis, and there we can actually see, okay, it's a bimodal distribution, so we have kind of two peaks over here, and there is obviously objects which have a low aspect ratio, and there's objects which have a high aspect ratio. And we can differentiate them by looking into this histogram. There's a local minimum in this histogram. And when we take this local minimum and kind of find the position, the Otsu algorithm could do that, right? So you learned that. Then we can differentiate suddenly elongated objects from round objects. Also here in this case, we have to train our algorithm on one data set and then look on another data set if it's still working. I'm just saying this is an alternative way of approaching similar questions. It's also a way of approaching very different questions. We have 1,000 parameters, 1,000 measurements out of our data. This is what Cell Profiler does, right? So we get billions of measurements out of billions of images, and we don't know anything about it. Then we use unsupervised machine learning to form our data into clusters and say, okay, these are obviously, they have the same property, they have a higher aspect ratio than those, and now we can start making conclusions about relationships between different parameters and so on. So we will not dig deeper into this. But if you want to read more about the typical terms for the algorithms behind our principal component analysis and cluster analysis. So this is, I would carefully say, not so much related to image analysis, coming from an image to a measurement. There we don't use this so often. But for the next step, for coming from image-based measurements to, for example, a clinical conclusion of which pharmaceutical works better than others pharmaceutical, this is an important research field actually. So this is what people work on. As a kind of summary at that point, yeah. So machine learning in the context of image segmentation takes the original image. We, for example, apply different convolutions or combined convolutions, like one image subtracted from another one. And we take these differently post-processed images and put them into a black box, which learns some model for making a prediction for us. So this is kind of the typical way of how we understand machine learning in the image analysis, in the image processing context. If we now remove this step here and make it part of the black box, we come to the point where we use convolutional neural networks. You may have heard these terms earlier. So we kind of do not make the decision anymore of what filters to apply in an image and select a certain range of these filters are applied and other filters are not applied. And now we take the results here and ask a machine learning algorithm for concluding something from that. If you also give the algorithm the freedom to design, for example, a filter matrix on its own and not just one of them, but maybe millions of them, we come to an algorithm group called convolutional neural networks, and this is part of deep learning. So this is the next step. There is amazing results in the recent years, but the number of applications in microscopy is yet a bit limited. I assume that this will change in the next 10 years. That's why I'm mentioning it here. So this may play a bigger role in the future. And if you want to evaluate the quality of deep learning algorithm segmenting your images, the technique for evaluating the quality is still the same as I showed you some slides earlier. So this is universal kind of in order to measure the quality of algorithms in this context. And I will not dig deeper into deep learning for now, but I wanted to give you a very rough but opinionated view on which algorithm or which class of algorithms is good in what and in what not. So manual workflow design, this is what you were just doing in the recent weeks. You blur an image and you look if the segmentation result looks good. And if not, you blur it a bit differently or you do another filter. You set up a workflow which solves your need, but it's you who makes the decision on how to do this. So that's kind of, we have in our hand of what is analyzed and how. So that's like in manual workflow design, that's super good. That's what we want to have. We want to define explicitly what is done in order to come to a measurement. In machine learning, the selection of which features are actually analyzed and come to a conclusion is semi-automatic. So you give some options to the software, and the software then automatically defines that rather these features are more important than other features. That's what the selection of the trees does for us. And then it will only take these features into account in making the decision. So it's semi-automatic. So there is some machinery doing this for you. In deep learning, this is fully automatic. So it's kind of, you give it an input image, you give it a ground truth, and then you say, go ahead. And it may do the right thing. Yeah? So it's technically, it's proven that it actually works. Yeah, so we specify the features and how to combine them. In the machine learning and in deep learning, we have to carefully check if the right features were taken or if reasonable features were taken. So we should actually, after we trained a model independent from machine learning or deep learning, we should actually check if the model is doing something reasonable. So for example, if we want to differentiate shape, and our model takes the position more into account than actually shape parameters, then there's a problem. And we should always think about that, and we should always try to find a way of how to do this. Furthermore, negative on the manual workflow design side, it's kind of obvious, the whole workload is on the human shoulder. So likely, and I'm speaking out of experience here, likely if I have a lot of work to do, if I have to design a lot of workflows, then the workflows will be worse than if I have to design only one workflow and have enough time to think about it. Yeah. So if the workload is on the human shoulders, then the quality may suffer or the number of tasks I can solve will suffer, but I cannot do both at the same time, right? So it's obvious. There's a lot of stuff to do if I manually design all my workflows. And on the machine learning, on the deep learning side, if the computer is busy, I turn on a second computer and I let two computers in parallel find a good solution for a particular workflow. And if two computers are not enough, then I turn on 100. I mean, this is where cloud computing comes into play, right? And the computational resources are there. So if we have a complicated problem to solve and we can keep 100, 1,000 computers busy for a week, we can just do that. And this is problems we cannot solve anymore manually. So therefore, that's an advantage, kind of, even though it also causes costs. So we should also think about it. Running an algorithm on 1,000 computers in the cloud for a week, this is actual money you're burning here. So, yeah, so in the manual workflow design, also in many machine learning algorithms, we can look into the model or into the algorithm and find out what it's doing. So if you wrote your image.json macro in a very good way, like I can read it, I can look into your workflow and I can find out what it's doing to come to a conclusion. And the same is true for machine learning for random forests. So I can read these forests. It's possible. It's like maybe it's not super easy and complicated, and there are 100 trees in the forest, but nevertheless, I can study the data structures inside and I can understand how a decision is made. In deep learning, it's not so easy. It's like the models are so complex and partly so big that you cannot tell anymore what it is actually doing to come to a conclusion. That's what I mentioned a bit earlier, is that machine learning and deep learning allow us to analyze data which is just impossible to analyze manually. So it's the structure of the data is so complicated. We have 4 billion images and thousands of parameters measured in these images. And we now want to know which of the parameters tells us something about the shape or tells us something about if this pharmaceutical is working or not. Manually, it's just not doable anymore. We have to take machine learning or deep learning algorithms into account for solving these kinds of problems. Deep learning algorithms usually use neural networks. Manual workflow design is done in neural networks, right? Don't forget that. It's the same technology, just a little bit differently implemented, but the algorithms behind are similar to some degree. And last but not least, and that's maybe the most important point on this slide, or maybe the most important point in this whole talk, all of them need training. So if you can program your workflow yourself after half a year training, fine, you have solved your problem. If you have to train a neural network for half a year in order to solve your problem, fine, you have solved your problem. But it all comes with training. And if you want to actually train neural networks, you have to teach yourself, you have to train training networks. So it's an additional step in basically the same thing. What I'm saying here is that artificial intelligence and deep learning and all these fancy algorithms which are out there, none of them solve a problem just like that. You have to actually train doing it, and you also may have to train a computer in doing it, and not just yourself. Okay, that's so far. In the next part, I will show you how to do pixel classification in Fiji. See you soon.